Friction is both a boon and a bane in our daily lives. Friction causes wear and tear in many of our mechanical systems, but it is also something that we take for granted. We need friction to keep things from falling. I'm sure you don't want your phone falling off your desk and getting a cracked screen, right? But what really is friction? Friction is a resistive force that an object experiences when it moves or tries to move relative to another object. Static friction plays a significant role in preventing objects from, say, falling off your desk. Every object in contact with another experiences some degree of static friction, as long as they are not moving with respect to each other. When forces from the surrounding cause an object to want to move, the surface the object is on exerts an equal but opposite force called friction, which causes it to stay. Exceeding the particular threshold, however, will cause the object to move, where instead of static friction we would have kinetic friction. This is the equation for static friction, where F is the amount of frictional force, mu is the coefficient of friction, which depends on the properties of the surface in contact, and N is the amount of normal force. From this we see that the amount of frictional force depends on the coefficient of friction and the normal force exerted by the two bodies. Increasing the amount of normal force with the same coefficient of friction increases the amount of frictional force. The same applies when it is done for the coefficient of friction. But how about changing the contact surface area? Why is that not in the equation? Let's find out. In this experiment, we examine if the contact surface area affects the amount of frictional force. When we place a brick on concrete, the brick will exert its weight onto the concrete. This, by Newton's third law of motion, will exert the same magnitude of force back onto the brick, otherwise known as the normal force. First, we tie a brick to a string with a load attached to the other end, which exerts a tensional force on the brick. The amount of tensional force depends on the weight of the load attached to the string. We keep increasing the load until the brick starts moving. At that point, the tensional force of the brick equals the critical threshold value for static friction. Then we investigate if changing the orientation of the brick affects the critical threshold value for static friction. This allows us to find out if changing the amount of surface area would have an effect on the amount of frictional force. On the first trial, the brick moves when we have about 2.43 liters of water. This is equal to 23.3 newtons of force acting on the brick. We repeat this 2 more times for consistency and average the results. Now let's change the orientation of the brick, therefore changing the contact surface area, and see what happens. What a surprise! The amount of force required to make the block move is still quite similar to the first orientation. So why did this happen? Since we only changed the orientation of the block, the weight of the block remained the same. Hence, the amount of normal force exerted by the concrete onto the brick also remains the same. Likewise, the surface themselves do not change, so the coefficient of friction has to remain the same, and according to the equation for static friction, if the normal force remains the same, and the coefficient of friction remains the same, the force of friction must also remain the same. However, this did not occur in all 3 orientations. In the third orientation with the lower surface area, we see that the amount of force required to make the block move was a bit lower than the other 2 orientations. This could have been due to the fact that the roughness of the wood block was different because of the grain of the wood, therefore resulting in a different coefficient of friction. Another explanation for this could be that since the block was standing up, the block actually tilted when the force was applied and fell rather than sliding across the concrete. If this did occur, then a lower amount of force would be required to make the block move. From the roof over our head to the bridges we drive our cars on, we are surrounded by trusses. These truss designs have become essential for almost all of our building and structures. Without them, we wouldn't have been able to build some of our most amazing structures like the Burj Khalifa. So, what exactly is a truss? A truss is a structure which consists of straight members connected together to make a framework. Trusses are generally made up of small triangles which allow for rigid and strong structures. The use of triangles in a truss have been proven to be much stronger than other shapes due to its low amount of elements. Because unlike polygons with 4 or more sides, triangles do not collapse onto themselves. Even though trusses are very strong and able to withstand large forces, there are still some points where they can fail. These points of potential failure occur at the members that experience the greatest amount of force. This is why we need engineers like us to calculate the force that act on each member and find out where the potential points of failures are to prevent catastrophic failures. But how do we calculate the forces acting on each member? There are 2 ways to do this. First is involving the method of joints. In brief, the method of joints involves taking the force at a single joint, resolving them into their vertical and horizontal components, and making the sum of the forces in each direction equal to 0, therefore giving us the force on each member at a particular joint. The second is using method of sections. In the method of sections, we take a part or a section of a truss and find the forces for the members that we split from the original truss. We can use the standard rules for static equilibrium, like the sum of the forces in the vertical and horizontal direction must be equal to 0, and the sum of the moments about any point must also be equal to 0 to find these forces. The basic principle of both these methods is that all members of a truss and the truss itself are in static equilibrium. This means that the resultant force and moment acting on the truss is equal to 0. Through the use of one or both of these methods combined, we are able to find the magnitude of the force in a member, as well as if the force in the member is a compression force or a tension force. So you may be wondering, what happens if the compression or tension force in a member is too much? Well, this is when we have catastrophic failure. Okay, maybe not so dramatic, but in theory this is what would happen. Generally in a truss, the member or members experiencing the greatest amount of force are most likely to be the first ones to break. This is what we set out to prove. For our second experiment, we decided, hey, why not build a truss and keep adding weight to it until it breaks? But before we could create our truss, we had to decide what material we were going to use. We'd have a couple of options such as cotton swabs, pencils, maybe even toothpicks, but we decided to go with popsicle sticks. We found that the structural integrity of cotton swabs and toothpicks was just too low, as they tend to bend when any force is applied to them. Pencils require too much force to break, making it hard for us to conduct the experiment easily. This is why we settled for popsicle sticks, as they did not require too much force to break, but just enough to conduct the experiment. We then created a truss using popsicle sticks and hot glue, as this allowed for the members of the truss to break rather than the joints when under pressure. Then we attached a plastic bag to joint B and C, as seen in the diagram, and placed the truss structure on two tables with a gap underneath for the plastic bags. We thought it would be best to use plastic bags to hold water, as the weight of a plastic bag is quite low, therefore we assumed it to be weightless. We then slowly added water into the plastic bags until one of the members broke. Here we can see a bit of bending in the truss structure. This could mean that the weight distribution of the water is no longer even, which may affect our final results. Due to the significant leaning of the truss structure, we have placed an extra support next to the truss to prevent it from having a large unbalanced force which could alter the amount of force on each member. At this point we have about 8 liters of water in the plastic bag, which amounts to 19.6 newtons of force acting downwards at joints B and C each, and the total weight force on the structure is about 78.5 newtons. We can now see that there is significant leaning of the truss structure due to the incredible amount of force on the truss. At this point we have about 12.5 liters of water, with one bag containing 6 liters of water and the other containing 6.5 liters of water. This provides a force acting downwards of 29.4 newtons at joint B and 31.9 newtons at joint C. Due to the large amount of weight attached to the truss, the box that the truss is sitting on starts to deform a bit. This causes some of the popsicle sticks to bend, therefore making the truss lean even more until member DG finally breaks, causing the whole structure to fall. The weight force on the structure at the point of failure was about 122.6 newtons. At the point where member DG broke, it was experiencing about 34.7 newtons of compression force. This was the largest force in the truss structure, which was experienced by member DG as a compression force and CG as a tension force. However, we suspect that due to the leaning of the structure, member DG could have experienced a bit more force than calculated, causing it to break first. After conducting the experiment, we found that what we expected to happen is what happened. The member experiencing the largest amount of force was the first one to break. However, we realized that due to the structure of a popsicle stick, the truss is most likely to break at the member experiencing the greatest amount of compression force. This is due to the fact that the tensile stress capacity of a popsicle stick is larger than the compressive stress capacity. This means that the popsicle stick is most likely to break under compression rather than tension, which is what happened in the experiment. Two members were experiencing the same force, except one was compression and the other was tension, and the member experiencing the compression force was the first to break. There were also some limitations to this experiment. Since we were using hot glue to stick popsicle sticks together, it is possible that there was more hot glue at one of the joints compared to another. This would have affected the force acting at a specific joint, therefore slightly exaggerating or understating the force in a member. However, we had no way of calculating this. It was also difficult to find supports that would be stable enough to hold the truss in place, while also being tall enough to prevent the plastic bags from touching the ground. This is why we had to stack multiple items on top of each other, which may have ended up affecting our results, as one of the items deformed a bit, which means it is possible that the truss may have been able to handle more weight. However, our final outcome was still the same as what we were expecting. This means that in a truss, the member experiencing the largest amount of force will most likely be the first one to break. Whether the member breaks under the largest amount of compression force or tension force is dependent on the material of the member. Thanks for watching. We hope you enjoyed our experiments.